Let us now find the solutions to generic linear SDEs using the Ito formula. So we will consider this kind of linear multidimensional time-varying stochastic differential equation, where dx is equal to time-varying matrix f of t times x times dt, where this f of t is assumed to be deterministic function. Then we have u of t times dt, where this u of t is again assumed to be a deterministic function of time. Finally, we have L, which is a function of t times d beta, and this L is again assumed to be a deterministic function of t. Then let's define a deterministic transition matrix psi t0 by the properties given below. So this is actually the classic deterministic definition of the transition matrix of a linear differential equation. Then we can proceed in a similar way as we would for deterministic differential equation. So we will multiply both sides of the equation by something called integrating factor, which is the psi t0t. So we will get this kind of equation, where we have already moved the term involving f of t times x dt to the left-hand side. But now we notice that the left-hand side is actually the Ito differential of psi t0t times x. So we can substitute this to the left-hand side, which gives us this kind of form for the SDE. So the Ito differential of psi times x is equal to psi u dt plus psi l d beta. We can now integrate in Ito sense from t0 to t, which gives this kind of equation. So we have psi t0t times x of t minus psi t0 x t0 is equal to the integral from t0 to t psi t0 tau u tau d tau plus then another term which is integral from t0 to t psi t0 tau l tau d beta. Now if we rearrange and recall the properties of the transition matrix, we get the full solution, which looks like this. We can now consider linear time invariant special case of these linear differential equations. So let's assume that our f is actually independent of time and L is independent of time as well, and we don't have any u term inside there. Now the transition matrix is just a matrix exponential, which is defined by the series property given over here. And now the solution simplifies to this kind of form. So x of t is equal to the matrix exponential of f times t minus t0 times x t0 plus then integral of the matrix exponential times L times d beta. And if you recall the heuristic solution that we obtained during the last lecture, this is exactly the same form, but now we have replaced that white noise times dt or white noise times d tau with d beta in the heuristic solution. For example, the solution of the Ornstein-Uhlenbeck equation looks like this. So the Ornstein-Uhlenbeck equation is dx is equal to minus lambda x dt plus d beta. So we can assume some kind of initial condition, and on the right we have the special case that the x0 is equal to 4. And this lambda is some constant and beta is of Brownian motion. So the solution is x of t is equal to exponential of minus lambda t, because we don't have any matrix exponential but only scalar exponential, times x0 plus then another term which is integral from 0 to t, the exponential of minus lambda t minus t tau times d beta. So the first term is deterministic given the initial condition, and the second term is actually a Gaussian random variable. Let's now take a brief look at what we should expect from nonlinear SDEs about the solution existence and then numerical methods. So first of all, there is no general solution method for nonlinear SDEs of this form. However, sometimes we can use transformation or some other methods from deterministic setting to derive a solution and replace the chain rule with Ito formula. So for example, you can try separation of variables kind of methods and then just replace those deterministic chain rules with Ito formulas. And it sometimes works. However, we still can use the Euler-Maruyama method presented last time. So if you take another look at it today, we can see that the increment on the right hand side was actually the increment of the Brownian motion. So the method now makes much more sense because we know that the increment is just the increment of Brownian motion which scales with square root of dt in time. The existence and uniqueness of SDEs can actually be analyzed with something called stochastic Picard iteration, which is related to the classic deterministic version of it. So we can consider the mean square convergence of these kind of iterates. The solution or the result is that the iteration will converge and thus the SDE will have unique strong solution provided that these conditions are met. So the functions f and l should grow at most linearly in x, and functions f and l should be Lipschitz continuous in x. A strong solution means that solution for x for given beta, meaning the whole trajectories, will be unique. But we can also define a weak solution so that there exists some pair x tilde beta tilde, where this beta tilde is a Brownian motion such that it solves the SDE. And weak uniqueness means that the distribution is unique. But we might not be able to construct a unique x for given beta. It is also possible to define the stochastic integral in another way. In so-called Stratonovich integral, we take the middle point of the small interval as the evaluation point instead of the starting point in the Ito integral. Stratonovich integral is denoted with a small circle before the d beta. So indeed, recall that in Ito integral, we had the starting point as the evaluation point, d star. But in Stratonovich integral, the nice thing is that the Ito formula or this corresponding Stratonovich formula reduces to the chain rule from the ordinary calculus. So the second order term disappears completely. However, the disadvantage is that the Stratonovich integral is not a martingale, which means that it's not a process such that the expected value of the process is given by the last chain value. This makes the theoretical analysis of the integral a bit harder. However, Stratonovich integral is very common in physics, mainly for the reason that smooth approximations to the white noise converge to a Stratonovich integral in certain sense. However, there's a simple conversion formula between Stratonovich SDEs and Ito SDEs, which is given like this. So if we have a Stratonovich stochastic differential equation of this form, where dx is equal to f of x and t dt plus l x and t times the Stratonovich differential of Brownian motion, then it's completely equivalent to another SDE in Ito sense, where we just replace the drift function f with a modified drift function. So the modified drift function is given below. You just need to modify it by adding a correction term, given here. So let's now summarize what we have learned. So white noise formulation of SDEs that we considered heuristically during the last lecture had some problems with the chain rule as well as nonlinearities and solution existence. However, it turned out that we can reduce the problem into the existence of certain integral of a stochastic process. We also saw during this lecture that the integral cannot be defined as a Riemann integral, Steltest integral, or even as a Lebesgue integral. However, it could be defined as something called Ito stochastic integral. Given the definition, we can define Ito stochastic differential equations by using their equivalent integral equation formulations. In the resulting Ito stochastic calculus, the chain rule is replaced with the Ito formula. And it turned out that for linear SDEs, we can obtain a general solution, and actually the existence and uniqueness can be analyzed analogously to the deterministic case. We also saw that there is something called Stratonovich calculus, which is obtained by slightly modifying the definition of the Ito integral, or the stochastic integral.